तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to Prestressed Concrete Structures. Today we are covering the fourth lecture of Module 3 on Analysis of Members. In today's lecture, we shall cover the analysis for ultimate strength for members under flexure. Under that, we shall understand the variation of stress in steel throughout the loading history, and we shall also learn about the condition at the ultimate limit state, and finally we shall move on to the analysis of a rectangular section. First, the analysis for ultimate strength. A prestressed member usually remains uncracked under service loads. The analysis under service loads assumes the material to be linear elastic. That means whatever we have studied till now for the analysis under service loads, we have assumed a linear stress strain diagram both for concrete and the steel. But after cracking, the behavior of a prestressed member is similar to a non-prestressed reinforced concrete member. With increasing load, the stress versus strain behavior of concrete becomes nonlinear. Close to the yielding of the prestressing steel, the stress versus strain behavior of steel also becomes nonlinear. This makes the analysis of ultimate strength different from the analysis under service loads. Under analysis of service loads, we have assumed both the materials to be linear elastic, but when we are doing an analysis for ultimate strength, there the concrete is nonlinear and it has gone into its inelastic region, and also the steel has moved into the nonlinear inelastic region if it has started to yield. The analysis of prestressed member for ultimate strength is similar to that of a reinforced concrete member. The analysis aims to calculate the ultimate moment capacity, which is also known as the ultimate moment of resistance. The capacity is compared with the demand at ultimate loads. In reinforced concrete analysis, we follow the limit state analysis where we find the ultimate strength of a member. The analysis of ultimate strength of a prestressed concrete member is very similar to that of the reinforced concrete member. And then once we find the strength, we compare it with the demand under the ultimate factored loads and make sure that the strength or the capacity is greater than the demand. There is an inconsistency in the traditional analysis at the ultimate state. The force demand is calculated based on elastic analysis with superposition for the different load cases using the load factors, but the capacity is calculated based on the nonlinear limit state analysis. Now, this inconsistency has stayed after the introduction of the limit states method, that when we are calculating the demand, we are using a linear analysis with the principle of superposition being applied for the different load cases, whereas when we are trying to find out the capacity, we are using a nonlinear behavior of the material. Now, this inconsistency is justified for the following arguments. First, the moment versus curvature relationship is almost linear till the yielding of the steel. That means, although there is some nonlinearity in the concrete, yet the nonlinearity is not reflected to a great extent before the yielding of the steel. Second, the moment at yield is slightly lower than the ultimate moment capacity. That means, when we are talking of the capacity, the almost linear behavior is up to the yield moment, which is slightly lower than the ultimate capacity. That is, in the strength axis, it is almost linear close to its ultimate capacity. The third argument is that the calculated moment demand for a load case is based on elastic analysis, that is well within the moment at yield. Say if I pick up the load case for the dead load, or if I pick up a load case for the live load, then the moment demand for any of this particular load case is well within the yield moment, and hence superpositions for the different load cases is applicable to find out the force at ultimate. Of course, superposition cannot be used to calculate the deflection at ultimate. That means, here we have to be careful that we may apply the principle of superposition to find out the demand which is in the force axis, but we cannot use the principle of superposition to find out the deflection at ultimate, because after yield there is a substantial deformation, and this plastic deformation will not be properly accounted for if we use the principle of superposition for deflection. The second important aspect of the analysis at ultimate strength is to understand the variation of the stress in the steel. In non-prestressed reinforced concrete members, the tension and consequently the stress in steel increase almost proportionately with increasing moment till yielding. The lever arm between the resultant compression and tension remains almost constant. We had seen this in the analysis under service loads, that for reinforced concrete member, as the load is increased or as the external moment is increased, the tension in the steel and hence the stress in the steel increases almost proportionately till it starts to yield. The lever arm between the resultant compression and tension remains more or less constant. Whereas in prestressed concrete member, then the tension and consequently the stress in prestressing steel increase slightly with increasing moment till the cracking. The increase in moment changes the lever arm significantly. So, this is in contrast to the reinforced concrete, that for prestressed concrete, as the load is increased or as the external moment is increased, the tension in the steel does not increase significantly, it just increases slightly, whereas the lever arm between the compression and tension increases as the moment increases. The compression shifts from the level of the prestressing steel upwards, and that increase in the lever arm is able to resist the increasing external moment. This was explained previously in the module of analysis under service loads. Now, after cracking, the stress in steel increases rapidly with moment. That means, before cracking, the increase in the stress in steel is not significant, but after cracking there is a significant increase in the stress in the steel, and then it reaches a value close to its ultimate. The following sketch explains the variation of the stress in prestressing steel, which is denoted as Fp, with increasing load. In this sketch, what we see is that first the prestressed member has been stretched with a stress of a value Fp0 in the tendons. Now, as the self weight is acting, it can act either while the member is hogging up, or it can act when the shuttering or the false work is removed. Now, when the self weight acts, there is a slight increase in the Fp0, and then with time there is a drop in the prestressing force due to the long term effects of shrinkage, creep and relaxation, and it stabilizes to a value of Fpe. Now, the drop in the prestress have been just denoted by a vertical line in the sketch, because we are not plotting this with respect to time. We are plotting the variation of the stress with respect to the increasing load. Now, from the self weight, once the service load starts acting, the stresses again increase slightly till the member cracks. Now, for a type 1 or type 2 member, the members do not crack, and hence the variation of the stress in the steel is very small, and hence it is neglected in the analysis under service loads. We assume that the stress in the steel remains constant at a value of Fpe. Now, after cracking, there is a sudden increase in the stress in the steel. Here you see that both for bonded and unbonded tendons, there is a jump in the stress in the steel. There has been a redistribution of the stresses between the concrete and the steel, and then when the load is increased further, the stress increases till it reaches an ultimate value corresponding to the ultimate capacity of the member. For bonded tendons, the stress is higher at the cracks, whereas for an unbonded tendon, the average stress over the length is not as high as the local stress for a bonded tendon. The above sketch assumes that the section is failing in flexure. Other types of failure are not considered here. The stress variables in the sketch are defined as follows. Fpe is the effective prestress after long term time dependent losses, Fp0 is the prestress after initial losses, and Fpu is the ultimate stress in prestressing steel corresponding to the ultimate capacity of the member. Now, let us try to understand this variation in a bit more details. When the pre-tensioned member is lifted from the prestressing bed, the prestress increases beyond Fp0 due to bending under self weight. For a pre-tension member, the self weight starts acting when the member is lifted from the prestressing bed. Now, if during the transfer of prestress, if the member hogs up, that means the prestress is high enough to counteract the self weight, then the self weight will of course be acting right after transfer. Now, for a post tension member, if the member is post tensioned in the casting bed itself, then the self weight may not act during prestressing. But if the post tension member is prestressed at the site where it is already being supported only at the edges, then the self weight is acting even before the prestress is applied. Hence, this increase from Fp0 to a value slightly higher than Fp0 is due to the self weight of the member. The time dependent losses over a period reduces the prestress to the effective value Fpe. The drop in the prestress is represented by this vertical line, and this occurs over several years over the service life of the member. Now, when the external load starts acting, the pre-stress increases slightly beyond FPE, the increase is higher in bonded tendons due to the local increase in stress at the region of higher moments. That means when the service load is acting, the stress will increase from FPE to a value which is slightly higher than FPE, and in bonded tendons the value is higher because the stress at the region of higher moments is higher than the stress in the region of lower moments, whereas for an unbonded tendon the stress is average throughout the length of the member. This increase in pre-stress is neglected in the analysis under service loads. After cracking, the stress increases rapidly till it reaches FPU. After cracking, as I said before, that the behavior of prestressed concrete member is very similar to reinforced concrete, and the stress in the steel increases quite rapidly till it reaches the ultimate value. The increase is higher for bonded tendons due to local increase in stress at the cracks. The stress is not uniform along the length for a bonded tendon. For a bonded tendon, the stress is higher at the regions of high moments, and after it cracks, the stress is higher at the location of the cracks. It is not uniform along the length. Whereas for an unbonded tendon, the stress remains uniform along the length. At the failure of the beam, it may not reach as high as the local stress for bonded tendons, and hence we observe that the stress that is achieved in an unbonded tendon is not as high as the local stress in a bonded tendon. Thus, we have understood the variation of the stress in steel as the load is increased. To summarize quickly, that the stress does not increase much during the service load, but after it cracks, the increase in the stress is substantially high, and we cannot consider that the stress is remaining constant at FPE. Next, we are trying to understand the conditions at ultimate limit state. In the limit states method of analysis, the limit state of collapse or the ultimate state of a member under flexure is defined as the state when the extreme concrete compressive strain reaches a value of 0.0035. This is the definition of failure of both a reinforced concrete member and a prestressed concrete member as per the Indian codes, that at the ultimate state, the extreme concrete compressive strain has a value of 0.0035. This is represented as epsilon Cu, thus epsilon Cu is equal to 0.0035 at the ultimate state. Depending on the amount of prestressing steel, a section can be under reinforced or over reinforced. For an under reinforced section, the amount of prestressing steel is less and the steel yields before the extreme concrete strain reaches 0.0035. That means the concept is similar to reinforced concrete, that in a reinforced concrete we had learned that an under reinforced section means that the steel will yield before the concrete reaches its ultimate strain. Here also we are saying that the steel will have substantial yielding before the concrete reaches its ultimate strain. For an over reinforced section, the amount of steel is high and the steel does not yield at ultimate. Just like reinforced concrete, we are defining an over reinforced section as that there will be no yielding in the steel before the concrete reaches its ultimate strain. Now, the transition situation is called a balanced condition, and we are familiar with it in a reinforced concrete analysis. Let us try to understand the profile of the strains at the ultimate for the three situations. For the profile at the left, at ultimate the strain of the extreme concrete fiber is epsilon Cu, and the strain in the prestressing steel is higher than the strain for balance. Now, here we can see that the linear strain diagram comes from the assumption that the plane sections remain plane till the failure, and next we have to also note the strain compatibility condition at the level of the prestressing steel. Now, here there is a difference between the reinforced concrete and prestressed concrete. In reinforced concrete, the strain in steel is same as the strain in the concrete at the level of the steel, whereas in prestressed concrete there is a permanent difference between the strain in the prestressing steel and the strain in the concrete. That means even at ultimate that difference will be there, and that difference is being denoted as epsilon DEC, or which is called the strain at decompression of the steel. The total strain in the prestressing tendon is equal to the strain in the concrete at the level of the steel plus epsilon DEC, and for an under reinforced section it should be greater than epsilon PU balance. On the other hand, if we look at the right diagram, there the strain in the steel will be lower than epsilon PU balance when the extreme compressive strain in the concrete is epsilon Cu, whereas the transition we are saying that it is a balanced condition where the strain in the prestressing steel is equal to epsilon PU balance. Now, in this previous sketch, epsilon DEC is the strain in the steel at the decompression of concrete, and epsilon PU balance is the strain in the steel at balanced condition. As mentioned under material properties, the prestressing steel does not have a definite yield point. See, here we are seeing a difference between a mild steel behavior in reinforced concrete and the behavior for a prestressing steel. A prestressing steel does not have a definite yield point like a mild steel. The 0.2% proof stress is defined when the steel reaches an inelastic strain of 0.2%. That means the 0.2% proof strain is like an equivalent yield point which is defined for a prestressing steel. We had learned about this when we studied the material properties of the prestressing steel. Hence, unlike reinforced concrete, the transition from under reinforced to over reinforced section is gradual and there is no definite balanced condition. In reinforced concrete, we had defined a definite balanced condition. We had, for a mild steel, we know a definite yield point. The code had given a certain value of the strain in the steel, which if the steel is equal to at the failure of the section, then we say that the section is balanced. But in prestressed concrete, we do not have any definite balanced condition because the steel itself does not have a definite yield point. IS 1343-1980 does not explicitly enforce an under reinforced section. It just limits the maximum stress in the steel, but the Indian Railway Standard Concrete Bridge Code requires that the strain in the outermost tendon is not less than the following, which is equal to 0.87 times the characteristic strength divided by the modulus of prestressing steel, which is as if the elastic component, plus a plastic strain of 0.005. Now, this above value can be considered to be the strain in the steel at balanced condition. That means, since we do not have a definite balanced condition, if we want to define a certain balanced condition, then we need to define a particular value of the strain which the steel should have when the concrete is reaching its final strain. Now, depending on the code, we can define a balanced condition, and here we see a value which is recommended by the Indian Railway Standard Code for the concrete bridge design. Next, we are moving on to the assumptions of the analysis at ultimate strength. The analysis of members under flexure for ultimate strength considers the following. First, plane sections remain plane at ultimate. This is the Bernoulli's hypothesis, which is the basic assumption in flexural analysis. The second is the perfect bond is retained between concrete and prestressing steel for bonded tendons. That means we assume a strain compatibility between the concrete at the level of the steel and the prestressing tendon till the failure of the member. This is not exactly true around the cracks where there is a disruption of the bond, but in an average sense we assume that there is a strain compatibility between the strain in the concrete and the steel. Third, the tension in concrete is neglected. This is an assumption to simplify our calculations. And the fourth, the design stress versus strain curves of concrete and steel are considered. In service load analysis, we are assuming a linear elastic behavior for both the materials. We just need to know the moduli for the two materials. But in the analysis for ultimate strength, we should know the full design stress strain curve for both the concrete and the steel. The method of analysis will be presented for three types of sections. First, a rectangular section. A rectangular section is easy to cast, but it is not an efficient section. Second is a flange section. A precast flange section with flanges either at top or bottom needs costlier formwork, but the section is efficient in flexure. A flange section can also be made of precast web and cast in place slab. Third, we shall also learn about partially prestressed section. There, a section in a member contains both prestressed and non-prestressed reinforcement. Now, the comparison of different types of sections will be again elaborated when we study the design of prestressed members. Here, we have just got some brief idea about the different types of sections. One type of section we shall study is the rectangular section, the other type of section is the flange section, and the third type of section is the partially prestressed section, which contains both the prestressed and non-prestressed reinforcement. Next, we are moving on to the analysis of a rectangular section. The following sketch shows the beam cross section, strain profile, stress diagram, and force couple at the ultimate state. Before we start the analysis, we should understand these individual diagrams. The important variables in a rectangular section is the breadth of the section, which is represented by B, the depth of the CGS, which is represented by D. Next, at ultimate, we first draw the strain diagram. We say that the strain is linear along the depth, which is from the assumption that plane sections remain plane. We also say that at failure, the ultimate strain in the concrete is 0.0035, and the strain in the steel is equal to the strain in the concrete at the level of the steel plus the permanent strain difference, which we are representing as epsilon DEC. From the strain diagram, we move on to the stress diagram. We denote the depth of the neutral axis is the level where the strain in the section is 0. The depth is represented as xu for ultimate, and in the stress profile we are having a nonlinear curve for the concrete, which we get from the design stress strain curve, with a maximum value of stress which is equal to 0.447 times the characteristic compressive strength. And the stress in the prestressing steel is denoted as FPU, which corresponds to the strain of epsilon PU. To determine FPU, we need the design stress strain curve for the prestressing steel. From the stress diagram, we move on to the force couple. The resultant compression is represented as Cu, which acts at a depth of 0.42 times xu, and the resultant tension Tu is equal to the area of the prestressing steel, which is denoted as AP, times the stress, which is FPU. The constitutive relationship for concrete that we use is parabolic up to a strain of epsilon naught, and then it is the stress is constant up to the ultimate strain of 0.0035. From the design curve, we can find out the expression of the resultant compression, and this expression is Cu is equal to 0.36 times the characteristic strength times the depth of the neutral axis times the width of the rectangular section, and the Tu is equal to AP times FPU, as I said before. Now, for the analysis at ultimate strength, we do it based on three principles of mechanics. First, the equation of equilibrium of the forces. The axial forces are under equilibrium, that means Tu is equal to Cu, which gives AP times FPU is equal to 0.36 FCK times XCU times P. Second equilibrium equation is that the ultimate moment of resistance is equal to the tension times the lever arm, and the lever arm is given as the depth of the prestressing steel minus the depth of the resultant compression, which is given as 0.42 xu. Hence, the lever arm is d minus 0.42 xu, and we can get an expression of the ultimate moment capacity, which is equal to Tu times the lever arm. Tu is equal to AP times FPU, and the lever arm is d minus 0.42 xu. The second principle that we use is the compatibility of strain, and which also involves the assumption of plane sections remaining plane. We are able to relate the strain in the steel with this ultimate strain in the concrete. By the similarity of triangles, we can write that xu divided by d is equal to 0.0035, which corresponds to the upper triangle, divided by the sum of the strains at the extreme compression fiber and of the strain in the concrete at the level of the steel, which is given as 0.0035 plus epsilon Pu minus epsilon DEC. Epsilon Pu minus epsilon DEC is the strain in the concrete at the level of the prestressing steel at the ultimate state of the member. This equation is the compatibility equation relating the strains in the prestressing steel and the strain in the concrete. The third principle that we use is the constitutive relationships. The constitutive relationship for concrete has already been considered in the expression of Cu. This is based on the area under the design stress strain curve for concrete under compression. For the steel, the constitutive relationship can be expressed as a function Fpu is equal to F of epsilon Pu, where F of epsilon Pu represents the design stress strain curve for prestressing steel under tension. That means we have seen this curve before under material properties, that given the design stress strain curve, for any value of epsilon Pu, we can determine the stress in the steel, which will be represented as Fpu. Now, in the analysis of a rectangular section, the following variables are given. We know the geometry of the member, that means we know B and D. We know the area of the prestressing steel, that means AP is known. We also know epsilon DEC, which is the strain in the prestressing steel at decompression of concrete, or which is the strain difference between the concrete and the steel at the level of the steel. How do we know that? I am explaining it later. We also know the material strength of the two materials, for the concrete, which is represented as FCK, and for the steel, which is represented as FPK. Now, what are the unknown quantities that we need to find out? The first one, what we are looking for is MUR, which is the ultimate moment capacity or the ultimate moment of resistance. Next, we have to know XU, which is the depth of neutral axis at ultimate. We also need to know epsilon Pu, the strain in the prestressing steel, and Fpu, which is the stress in the prestressing steel at the ultimate. The objective of the analysis is to find out MUR from the equations that we have in our hand. The simultaneous equations 3D1 to 3D6 can be solved iteratively, and this procedure of analysis is called the strain compatibility analysis. The steps are as follows. First, we assume a depth of the neutral axis, which is XU. Next, we calculate epsilon Pu from equation 3D5, which is the strain compatibility equation. By rewriting the equation in a slightly different form, we can find out that epsilon Pu is equal to 0.0035 divided by XU by D. Since we know XU, we know the denominator, then this term minus 0.0035 plus epsilon DEC, which is also known. The third step is calculate epsilon FPU from equation 3D6, which is the design stress strain curve for the concrete. That means once we know epsilon Pu, we can calculate Fpu. Calculate Tu from equation 3D2. The Tu is the total force, which is equal to the area of the prestressing tendon times the stress. Next, we calculate Cu from equation 3D1, which is Cu is equal to 0.36 FCK XUB. Here we are using the design stress strain curve of the concrete, and then we check the first equilibrium equation, which is 3D3, that whether Tu is equal to Cu as per our calculations. If it is not satisfied, then we have to change XU. If the calculated Tu is less than Cu, then decrease XU. If the calculated Tu comes out greater than Cu, then increase XU. That means if Tu is less than Cu, we should reduce Xu so that we have less compression in the concrete and more tension in the steel. But if the calculated Tu comes out to be greater than Cu, then we have to increase Xu, that means give more compression in the concrete and less tension in the steel. Now we do this iteration process till the values of Tu and Cu are reasonably close, and once we have converged to this situation, then we calculate MUR from equation 3d4, which is given as TU times the lever arm. The capacity MUR is then compared with the demand under ultimate loads. In the strain compatibility method, the difficult step is to calculate XU and FPU, which we have to do in an iteration process. IS 1343-1980 allows to calculate these values approximately from table 11 and table 12, appendix B, based on the amount of prestressing steel. The latter is expressed as a reinforcement index omega p. That means the code gives us a simple way to calculate the depth of the neutral axis at ultimate and the stress in the prestressing steel at ultimate, but these values are approximate. These values are given in two tables as a function of a variable which is a reinforcement index omega p, which is equal to the area of the prestressing steel times the characteristic strength divided by the area of the concrete section, which is B times D times the characteristic strength of the concrete. Now, the tables give the values for this type of sections. Table 11 gives for pre-tension members and post-tension members with bonded tendons. Table 12 gives the values for post-tension members with unbonded tendons. As I had said earlier, that the analysis of pre-tension members and post-tension members with bonded tendons are similar because we assume strain compatibility for both of them, whereas the analysis for post-tension members with unbonded tendons is different because there we cannot assume strain compatibility at a section, we assume a compatibility of the overall deformation of the member. To understand the tabulated results, this plot shows the values of FPU, which is given, which is normalized with respect to the maximum allowed stress 0.87 FPK in table 11, and these values are given with respect to omega p. As omega p increases, we observe that beyond a certain value FPU will reduce. That means if we put more and more steel beyond a certain point, the stress in the steel will go down, and that is quite understandable. On the other hand, if we are trying to reduce the amount of steel, then the stress in steel will go up till it reaches the maximum value which is allowed by the code. The code does not allow the stress in the steel to go beyond 0.87 FPK. On the other hand, if we try to understand the variation of the depth of the neutral axis, then as the amount of steel is increased or as omega p is increased, the depth of the neutral axis also increases, because if we have more and more steel, we need more and more concrete to balance the force in the steel, and hence the depth of the neutral axis also increases with the increasing amount of the reinforcement. Thus, the values given in the table, although they are approximate, they follow our intuition of the behavior of the prestressed concrete members. Next, we are trying to understand the analysis of a rectangular section with the help of an example. A prestressed concrete beam produced by pre-tensioning method has a rectangular cross section of 100 millimeter times 160 millimeters, which is breadth times the total depth. It is prestressed with 10 numbers of straight 2.5 millimeter diameter wires. Each wire is stressed up to a load of 6.8 kilonewtons. The design load versus strain curve for each wire is given in a tabular form. The grade of concrete is M40. Estimate the ultimate flexural strength of the member by the strain compatibility method. The given section is rectangular. Here the wires is given in from which we can find out the depth of the CGS, which is 40 millimeters below the CGC, and the grade of the concrete is given, which is M40, and the design load versus strain curve for each wear is given. This is different from the stress strain curve, because sometimes the load versus strain curve is readily available from the tests, and that can be used to calculate the ultimate strength of the member. The design load versus strain curve is given in a tabular form for the range under consideration. Here we are not mentioning values outside this range because we do not need that in our calculation. Say for a strain of 0.006, the load in a wear is 5.4 kilonewtons. Similarly, for a strain of 0.014, the load is 10.7 kilonewtons. In the solution, first we are calculating the initial strain in the prestressing wears epsilon pi to calculate the strain at decompression of the concrete. Since we know the initial load in each wear, we can calculate the strain from the given load versus strain table, and that strain has come out to be 0.0073. Since for a pretension member the strain at decompression is same as epsilon pi, we can write that epsilon DEC is equal to 0.0073. That means given the prestressing force, we are able to calculate the strain at decompression, and this is a quantity which is known to us. We also know the depth of the CGS, which is equal to 120 millimeters. We are using the strain compatibility method to solve this problem, and the strain compatibility method is an iterative procedure where we start by assuming a depth of neutral axis. Now this iterative procedure can be nicely written down in a tabular form to have the results in a nice compact way. Now in this table we are first writing the assumed depth of neutral axis, which is xu, then we are writing the normalized value xu by d. From the compatibility equation we can find out the strain in the concrete at the level of the steel, which is epsilon pu minus epsilon DEC. Once we know this, we can calculate the strain in the steel, because epsilon DEC we have already calculated. Then from the strain we are calculating the load. See, here it is different from a conventional analysis. Instead of calculating the stress, we are calculating the load, because the load is given in the form of a table. Now once we know the load in a single wear, we can find the total tensile force in the tendons, which is 10 times the load in a single wear, since we have 10 wears. And we can also calculate the compression, because once we have assumed the depth of neutral axis, we know the expression of the compression. And then we are checking the first equilibrium equation, that what is the values of Tu and Cu with respect to each other. What we find is we first started with a assumed depth of 60 millimeters, which is half of the effective depth. Xu by d is half, which is 0.5, and from there we find that the tension is 94 kilonewtons and the compression is 86.4 kilonewtons. For this step, the tension is greater than the compression. Hence, we need to have a larger Xu to give more compression in the concrete. We are increasing Xu to 65 millimeters, for which Xu by d is equal to 0.54. Again, going through the steps, we find out the tension to be 91. The tension has now dropped from 94 to 91, whereas the compression has increased from 86.4 to 93.6. And here we find that the tension is lower than the compression. That means at this stage we should reduce XU to give more tension in the tendons. After a few iterations, we have come to a value which is 63.5 millimeters, for which we find the tension to be 91.5 kilonewtons and the compression to be 91.4 kilonewtons, which are reasonably close, and we can say that the evaluation of the depth of the neutral axis and the forces have converged at the final values. The ultimate flexural strength is thus given as the tension or the compression times the lever arm, and we know all these variables. Once we substitute these variables, then we find out the ultimate flexural strength of this pretensioned member. Thus, in today's lecture, we studied the analysis of members for ultimate strength. First, we understood the variation of stress in the steel. In our analysis for service loads, we did not consider any variation in the stress in the steel. We said that the stress is constant at the effective pre-stress FPE. Today, it was justified that what we observe is that before cracking, the increase in stress with increasing load is very small, and hence we can neglect the increase in stress. It is only after cracking that the stress in steel increases suddenly, and as we are approaching the ultimate strength, the stress will increase quite rapidly. Now, next we also understood the conditions at ultimate limit state, that how do we define the ultimate limit state of a member under flexure. We said that it is defined based on the strain in the extreme concrete fiber to be 0.0035 as per our Indian code. Now, during that, if the steel has substantially yielded, then it is called an under reinforced section. But if the steel hasn't yielded when the concrete has reached its ultimate strain, then it is called an over reinforced section. For a pre-stressed member, there is no definite balance point because the steel itself does not have a true yield point. We may define a balanced condition by considering a particular value of strain which the steel should have when the concrete attains the strain of 0.0035. Next, we learned the analysis of rectangular members. What we have seen that in the analysis, we first draw the strain diagram where we assign a strain of 0.0035 for the extreme concrete fiber under compression. From the strain diagram, we draw the stress diagram based on the constitutive relationships. For the concrete, it is a nonlinear behavior. For the steel also, it is a nonlinear behavior at ultimate. Now, once we know the strain diagrams, we can draw the force couple. We have three principles of mechanics working. The first is the equilibrium of forces. The first equation is the equilibrium of the tension and the compression. The second is the equilibrium of the moment, from which we have an expression of the ultimate capacity. We have the compatibility equations and we have the constitutive relationships. Now, these equations can be solved iteratively by a strain compatibility method, where we start with an assuming the depth of the neutral axis. Now, if we want to bypass this strain compatibility method, we can use the code tabulated values of the depth of neutral axis and the force in the steel, from which we can evaluate the ultimate moment of resistance for a rectangular section. In our next section, we shall move on to flange sections and partially prestressed sections. Thank you.